So today we'll talk about random sampling, but applied to low-dimensional geometry, things like disks and points in the plane and things like this. Uh, uh, and a really, actually very nice idea. So, okay, some things we'll get exposed to. So the goal is to really obtain these what are called epsilon samples and epsilon nets. I'll note that besides applications in like comp geometry, this is also very important for learning theory. We'll talk about that more throughout the week. We'll be using what's called the additive Chernoff inequality today, so I'll show that. And then we'll mostly try to analyze this. I think this discussion of VC dimension will probably happen on Wednesday, but maybe I can get it started today. So, okay. So, in general, we've used this many times now, but if you have these independent random variables and they're bounded, so say now they're scaled to be between 0 and 1, then the odds of being close to the average is very high when the average is large or moderately large, because the probability of deviating from the average is exponentially small in the average. And so, right, this would be the exact one for the multiplicative. So additive is a little bit different because we're going to be looking at plus epsilon, minus epsilon kind of thing. Okay. But the form is kind of similar. So here I'm taking the average of n 0, 1 random variables. Um, they could also have been between -1 and 1. That wouldn't really be very different. And said, okay, the odds of being off by epsilon, if you sort of divide by n, okay, so the odds of being off by 5% will be -2 5% squared times n. Okay. It's sort of a similar form to multiplicative Chernoff if you think of like clearing out the n's on each side and you have like an epsilon here and sort of something that looks like epsilon n up there, but okay. So that is the additive Chernoff, and we'll use it today. And that'll give more intuition. Yeah, the joke is that we'll do the proof at the end if time permits, which we could. Um, yeah, somehow being forced to teach within 50 minutes made me clarify what I care about more than others. Okay, at some point I'll probably do one of these. All right, so to compare and contrast, these two bounds, yeah, they're kind of similar, but they're kind of different. But I thought if I put them side by side, it would be illuminating. Okay. Um, yeah, yeah. Okay, so that we'll need, and I'll put it in like the bottom corner of the slide so you don't have to memorize it. Let's talk about trying to do these epsilon nets and epsilon samples and also setting them up. So, okay, here is the abstract setup. Okay, I'm not sure sometimes if this terminology is helpful, but it's the convention. So we're going to be looking at like points and then like subsets of points, which we call for some reason ranges, I think because of range searching. But we'll be studying subsets of points that are like nicely have certain structures. For example, points could be points in Euclidean space, and ranges could be like all disks, right? Or roughly all subsets of disks. You have endpoints, and you put a disk there, it contains some points, it doesn't contain all others, right? In an extreme case, a range could be all possible subsets. That's not much structure. Yeah, it's called ranges because you might do range queries and stuff. So, so that's just some terminology, some examples, right? P could be a set of points on the line, and R could be intervals. Okay, so you see some points on a line, and each of these kind of red things is some interval around some subset of points. Okay, and we really care about which points are in the interval. So if two intervals, they have slightly different endpoints, but they contain the same set of points, they're basically going to be equivalent as far as we care. Okay, so it's really the kind of the subsets induced by intervals. So that's one example. Another example that I mentioned earlier, yeah, you have points in R2 and then a set of all possible disks. Okay. Another example. A third example are half spaces. So, I mean, I can only draw two-dimensional pictures. So here is there's a line splitting the space in half, and the highlighting is like that side of the line. Yeah. They don't have to be, but today all the examples are. We're going to be studying certain properties when R is nice and natural and stuff, and those often are convex, but they don't have to be. Yeah, yeah. Okay, but those are just examples of range spaces. Obviously, this is of interest to geometry people. This is also of interest in machine learning if you're trying to do classifiers where you're trying to split the point set in half, things like this. Okay, so in this world of range spaces and range queries, the kinds of queries you might ask and you might want to have a data structure for or something, some server for, are as follows. Okay, you have some point set and then you have like a disk in the plane and you say, okay, are there any points in this disk, right? Is it empty? That's a natural query. Another query that comes up is how many points does it contain, right? That will also come up often. Can you list the points that are in it? And another one is it's sort of like a heavy hitter question. Uh, does this disk contain at least 5% of all the points? Okay, what are the heavy disks? So these are like typical questions that you might want to ask. Okay, all of these questions can be formulated in terms of what we're going to call measure. Okay, so once you have a fixed point set, then I can say, okay, the measure of a range is the fraction of the points that it contains. So the numerator is the intersection, how many points are in the range R, how many points are in the disk, out of the total number of points. Okay. Today, I mean, just to keep things simple, everything's going to be with a finite point set, but it easily extends to like, oh, you have a distribution of points, and then that would just be, what is the probability that a random point from your distribution is in this range. Okay, good. And we're also going to be looking at, we'll get there in a moment, but at some level we're going to try to sample points and try to preserve the measures of all the ranges. Okay, so we're trying to get good representative samples. So if I have a subset Q, I'll let mu sub Q denote the range relative to Q. Okay. So that's the fraction of Q that lies in this range R. Okay, sorry, I feel like instead of doing something fun, we're just doing terminology. So the basic question is, you have a point set and you have all these shapes. And your high level goal is to preserve the measure of all the shapes. Right? And the question is, how big does my random sample need to be to ensure that these are roughly equal? There's different ways to quantify this that's coming up. Right? But this happens I mean, this, you can imagine this being natural. You're a telephone wireless company, right? And you can place towers anywhere. They induce some disk capturing a certain population of people, right? And if you could take your population and sample a smaller set, so you're doing a placement problem. Oh, I can place 5 things and I want to cover something like this. If you can sample down the number of people and still preserve, roughly how many you're covering all the time, you have a smaller problem to work with, right? So any geometric problem, okay, I can get a smaller representative data and work with this, right? In learning theory, some algorithms, not necessarily the best algorithms these days, but classical algorithms, if you look at them closely, they're roughly taking a point set maybe in a higher dimensional space and basically encapsulating one side or the other as like, oh, all the positive labels are in this disk, everything outside is not, or all the positive are on this side of the hyperplane, everything else is on the outside, right? So if you can kind of if P is originally like all the data samples ever in the world, right? Or, this could have easily been an infinite thing. So it's a distribution of data. And Q is your finite sample of training data, right? You want to make sure that every half space looks roughly the same. So the good half space classifiers still look like good half space classifiers on your smaller sample, right? So if you had this kind of property for your particular machine learning algorithm, then that would justify taking a smaller sample and just trying to optimize over this sample. Okay? Yeah, so mu should be kind of the fraction you get correct. So there's lots of applications. So, okay, how do we quantify that they're similar? We'll look at two today. We'll look at one in detail. So one epsilon sample means you're epsilon close additively. So like you're within 1% error for every single shape. Okay. And okay. The second one is sort of the heavy hitter version. It's called an epsilon net. And this is just saying I want to make sure that uh, uh, if a range is big in the sense that it contains at least an epsilon fraction of the points, then I have at least 1 point. Okay. So this will come up when mu represents like the mistakes made by a learning theory algorithm. So you want to make sure that any sort of learning hypothesis that makes a lot of mistakes, you find at least one counterexample in your data set. Yeah. No, this can be infinite, but we're going to come back to this point. But it could be like a fixed set of points in space and all possible disks. Infinite, or they could be infinite. I won't restrict it. And then everything we do today, you can even take P to be like a distribution of points. That's not too hard as well. But let's say the points are finite, but we're gonna dwell on exactly the question you asked. So first, I want to point out this: if you don't make any assumption on the ranges, the shapes, right, the classifiers, then if I wanted to say get an epsilon sample, then it's impossible to make Q much smaller than P. Why? R can be 1 point, but that would actually be okay because that would just be like mu would be 1 over P, 1 over N, and then mu sub Q would be like either, could be like 0, right? So 1 is actually okay. So I want to show that, okay, if Q is, say, smaller than 1 minus epsilon P, there must be some range I screw up for some, yeah. So the claim is that if I don't make any assumptions on R, then this is impossible. Yeah. Yeah, your range could be all the points on Q. So if I take R to be all possible subsets, right? So there's no structure. Then, yeah, the complement of Q. Okay, this has at least epsilon fraction of the points, but you sampled none of them, right? So that's the same for the epsilon net. That's the heavy hitter thing, right? So we really need to think about, oh, are there some nice structures, right? Like this is yes about random sampling, but it's also about understanding the value of structure in these sets. Okay, so. Okay, now for some of those examples above, like disks in the plane, uh, you can't actually induce all possible subsets of points, right? So take these 4 blue points, right? And you know, so my bad case was all possible subsets of points. And I can take a disk and I can, capture one of them at a time, like that. I can capture the bottom half, right? I can make that subset, that subset, that subset, that subset. But if I try to get like opposite corners, if I kind of only wanted to like get these two but not these two, I can't do that with a disk. So that is so with a disk, I'm worried about trying to preserve the weight or the measure of these subsets, right? But if my range space is all the disks in the plane, it actually only induces much smaller than all possible subsets in the plane, right? So that's good. That's good for us because it thwarts the counterexample from before. In fact, how many subsets of points can I make out of disks? Is that what's coming up? What is the point of this? Oh, yeah. How many can I do it? N square ish. So I think if you have 3 points kind of pressed up against the sides, that will define a circle. And if I have a circle containing like the 3 outer points, then I can kind of shrink it so that 3 points become on the border, right? So each circle is going to correspond to some combination of 3 and then everything that's inside. So it's like n cubed, right? So if I'm doing disks in a plane, I only need to preserve n cubed points if there's n points to begin with. Okay, so what's here? Okay, so I need a little bit of notation. So one key idea is this. If I have a subset of points Q, right, and I have all the disks in a plane, and I'm looking at their intersection with Q, there's only even fewer unique disks in a sense relative to Q. Because if two shapes have the same number of points in Q, then same set of points in Q, then they're equivalent as far as I care. As far as I care. Okay. So we'll use this notation. I guess I'll use like R and Q to mean, oh, let me project all the shapes onto Q. Let me take all the sets R and look at the intersection with Q, and then the corresponding set. Okay, so that's just one important notation. Okay, now let's look at this function. It's called the growth function. So there's some question of, okay, let's say that I have n points, okay, and my range space is the set of all disks or something. How many different ranges effectively can I create projecting onto Q over all possible endpoint sets? Okay? So with disks, any set of 10 points can generate at most 10 cubed, really distinct disks. After that, they get redundant. Okay, so we'll call that a growth function. So relatively simple, well-behaved natural shapes might have growth functions that are much better than 2 to the n. 2 to the n is all possible subsets. So most of the stuff we'll do today is focused on what happens when G is like a polynomial in n. There's some kind of lower complexity than usual. So, is there anything down here? Yeah, that's right. Yeah, so disk will give you like n cubed. Okay. All right, so we're going to try to do something parameterized by growth function in this class. So if a range space has low growth function, I want to get a really small sample and preserve all the weights. Okay. Okay, so let's do some preliminary calculations. So let's say that I sample k points with repetition or something. Okay. And I just want to look at a single range R and try to analyze, okay, what are the odds that I screw up by more than epsilon? Right? This is the fraction of the points that land in R compared to the fraction of points I expect. What are the odds that this is greater than epsilon? How would I do this? For every single point, look, yeah, so compute the probability that it's in Q. That is one approach. Yes. Yeah, okay, so I can make if P has n points, I'll make like n indicator variables. Now, okay, but now each indicator variable is, I guess, between 1 and k, because a point can get sampled k times. So if something gets sampled 3 times, it counts as 3. That'll get you a good average. But I'm trying to figure out, I want to show that I want to analyze probability of error. I'm, I'm analyzing, divergence from the mean. So the average, that will get you the average correctly, but I want to show that, I want to do a concentration kind of thing, right? Sorry? Yeah, okay, I didn't call Hofting, but we can try to use this. So if we're going to use the additive turn-off balances, this is the form we want, right? Plus epsilon, minus epsilon. I'm even using the same mu, so that makes it easier, right? But then I have to figure out what my xi should be. Sorry? Is the first sample point in it, is the second sample point in it. Slightly different, but similar. But this will guarantee it's a 0, 1 random variable. Okay, so if we just write out what mu q is, right? And we start applying this, so all I've done is expand out. Okay. And if we apply the additive turnoff directly, it's 2 because it's the absolute value. So I'm taking the union bound of being bigger by epsilon and smaller by epsilon. And is there anything over here? Yeah. Okay, so this is just applying the additive turnoff, right? Now, if I want to take the union bound over all ranges, I need to count how many ranges there are and pay a logarithmic factor in this, right? So let's say P had n points to begin with. How many sets do I need to take a union bound over? This g of n. So we can apply this growth function, okay? And what does that tell you? Apparently nothing on this slide. That if you take k to be about a logarithm in the growth function, so how many ranges there could be as a function of the original point set, then it probably is not an epsilon sample. I'm just taking a union bound, right? This kind of thing. And then you can see that we've chosen k to kill off the g term. Okay. Okay, so this is not such a big deal. All we've done is apply concentration to the sample, and then when we did the union bound, we substituted the growth function, right? So this comes back to your question of how many disks are there. Well, at some level, there can be an infinite number of disks, but if there's a finite number of points, then it's kind of implicitly bounded. Okay, good, good. So that's all to set up the following. What's going on here? Okay. So something similar. Epsilon net was, making sure you get at least 1 point from every set that's an epsilon fraction of your whole thing. So similarly, we can do the same calculation, pay a logarithm in the growth function. Epsilon squared goes down to just epsilon, because what you're doing is a little bit easier. Okay. So that's all fine and dandy. The question is, can you do better than this? So right now, this is just paying a union bound over all the ranges in the input, effectively. Can you do better? Um, but you still need the same number k, even if it was without repetition. Okay, so the answer is yes. So here's one bound. So, so it's presented a little bit funny, a little recursively. So it says if k is at least the growth function of 2k, the logarithm of that over epsilon squared, you'll get an epsilon sample with constant probability. Okay, what does it mean when k is greater than or equal to log of growth of k? So let's plug in g of n is equal to n to the d. So for disks in a plane, d was 3. So what if the growth function is a polynomial and d is the exponent? Then uh, k is at least, uh, if you set k to be at least d log d, then you'll find that k is at least log k or log g of k. And so it's saying that, for a disk, you only need 3 times log of 3 over epsilon divided by epsilon squared points to approximate everything up to an epsilon factor. Okay, so disks in the plane, if 1 over epsilon is a constant, you only need a constant number of points, right? And you get all disks, right? This is completely independent of the input size p, right? It's totally a function of the geometry encoded in this d. So d is some kind of complexity of the range space, right? Higher d, higher growth function. So disk in the plane, completely independent of the input size. That's right. That's right. I'm not sure how much is hiding in the big O, but that's right. I mean, I think the big O is probably like 4 or something, probably actually. Yeah. Because I think you're just coming from additive turn off bound. Yeah. I can't promise that my lecture notes do 4, but that's okay. So you can see why this is appealing to like machine learning or something, right? Because P is supposed to be an infinite set of data samples over, you want to generalize to everything. Saying, okay, if my classifier has a simple geometry and an effectively small d, then a relatively small finite sample set, if I learn it perfectly, I'm done. I have some kind of guarantee. Yeah, we'll make that more formal next time or Friday. Yeah. But the excitement is that this result is independent of the size of the point set. That means it's also effectively independent of the size of R, right? It's more a function of the complexity of R. Yeah, yeah. So it's about the complexity of R, yeah. Okay. Um, same improvement for epsilon net. So this is where you want to hit every range that's big. The real point is that you're going to get something independent of p. The epsilon squared becomes epsilon. And somewhere, for some reason, log of d over log of d disappeared. But anyway. But again, you're going to get a sample size independent of the number of points. Okay, good. All right, any ideas for how to prove this? I mean, just for fun. Yeah. Somehow this g of 2k is a hint, right? It's just a set of ranges induced by 2k points. I'm not sure if this is guessable. Uh, that's actually going to be quite close to the truth. Yeah, is there something where like, I don't know, I can sample k points first, that induces g of k points, and then can I check to see if another sample of k points preserves all of those pretty well, right? Then I would need to pay like log of g of k or something, right? That's actually going to be quite close. Um, yeah. Let me just try to explain. So, okay. So the setup is as usual the most important part. So first let's let Q1 sample K points. Okay. And I want to say that what are the odds that Q1 gets some range wrong? Okay. I want this to be at most 1/2 or something. Okay, so this is just one sample of K points. Ultimately, okay, I haven't done anything. That's of course what we wanted to analyze. So here's something. Here's maybe I mean I think this is a very creative, beautiful result. So here's maybe one point of inspiration. Huh? Where is it? Oh, rats. Okay, let's do a second sample of K points. Okay, just as suggested. I'll call that Q2. And now let's look at what are the odds that Q2 messes up or is different from Q1 on some range. Okay, so notice here that we're comparing mu2 to mu1 instead of mu2 to mu. The advantage of this is that once I'm looking at mu1, there's only, g of k unique values in mu1. So mu1's only really concerned with g of k different ranges. So there's some hope to union bound over this. Okay. How do I what? Ah, okay. Yeah, we're not done yet. Yeah, there's more clever things to come. Okay. And then I'm gonna let C be the event of both. Okay. So okay. So this is saying, oh, there's some range where mu1 screws up, oh, convert to a true one by at least epsilon and at least epsilon over 2. Okay. For some range. Okay. Anything down here? Okay. So the claim, we're going to use C in the proof. The claim is that the probability of event A happening is at most 2 times the probability of event B. So event A is what we're worried about. That's mu1 screwed up. Event B is mu1 and mu2 are off by epsilon over 2 for some range R. Okay. You might hope that event B you can get a better bound for because there's seems to be a limited number of distinct ranges at play. Once I fix, Q1, there's only so many ranges I have to worry about for Q2. Things like this. Okay. So if I can up to a factor of 2 turn event A into event B, that'll be a huge victory. Okay, so how do we do this? Okay, well, okay, this is very clever. So I'm first going to write probability of B. Okay, is at least the probability of event C. Okay, and event C includes event A. So probably event A and C happening at the same time. And we can write this as probability of C given A times the probability of event A. Okay. So, yeah, what is the probability that, yeah. Okay, so somehow this seems subtle. Okay, so, Okay, so we want to analyze probability of C given A. Okay, I want to argue this is at least 1/2. Okay, so what does this mean? This is the probability that, okay, so let's put it this way. So suppose A, so that implies that mu1r minus mu r is greater than epsilon for some r. That's just a definition, right? So let's just fix that r. So there's some particular r, right? And say, okay, what are the odds that mu2 and mu1 are differ by more than epsilon? So what's the intuition at least? I want to argue that this event is like at least 1/2 or something, right? So I want to argue then that mu2 and mu1 are probably off from each other on this particular range R. So what's the intuition? So mu2 is independent. So mu2 probably gets R correct. And mu1 already got R wrong. Okay. So this is really, okay. So we have mu2 of R minus mu R is at most, say, epsilon over 2 with good probability, right? Like probability at least 1/2. Just from the calculations from before. Before we were even taking a union bound over everything. So this is just one set, right? And if that's true, then mu1r minus mu2r is at least mu1r minus the true mean measure minus mu2r minus the true measure. Running out of space as usual. So you get epsilon minus epsilon over 2. Okay. So one of them is off by more than epsilon. The other one is probably within epsilon over 2 accurate. So they must differ by at least epsilon over 2. Okay. So then that will give you that this thing is at least 1/2. This is at least 1/2. Okay. And then you plug that back into here. That's the 1/2, right? And that's what you're looking for, right? But this is like really clever, right? Yeah. Because K is going to be big enough. So the same calculations we did from before. So in fact, by additive turnoff, K is going to be big enough that mu2 is probably going to be accurate for one range R. In fact, we're going to choose K big enough to be big enough to take a union bound over many ranges R and stuff like this. So yeah, this is just one set. Yeah. Okay, so this is like extremely clever. Okay, so with that in hand, um, I guess I probably want to show this is at most 1/4 or something. Okay, some constant. So if we can show that the probability of event B happening is small, then we're done. Yeah. Yes, but they're independent samples. You can. You could apply it more. Um, oh, remember, we're trying to show that mu2 and mu1 are actually far apart. We showed that mu2 on this range R, mu2 R minus mu1 R is bigger than epsilon over 2. I guess I greater than equal, but that's the same. So you on any particular range, they're probably going to be very close because they have similar distribution, right? And the original thing is, what are the odds that the first sample gets some range wrong? The second one is, what are the odds that the first sample gets some range wrong? The event C gets some range wrong while the other sample is similar, but that would require both samples to get it wrong, basically. Okay, so now I just have to analyze event B, which is what are the odds that there's some range R where the two samples disagree by at least epsilon over 2. Okay? We already see some of the intuition. If I imagine doing one sample before the other, then I sample Q1, and then I only have to check like a smaller number of ranges for mu2. Now the tricky part is, well, it's still kind of tricky, right? Like to actually prove this thing. Any ideas for how to prove this thing? Oh, that's also actually an issue. Yeah. So actually, yeah, the ranges for Q1 and Q2 are also different. Yeah. Okay. Well, anyone want to make a suggestion? Because the first step is the most important one, probably. Yeah. Yeah. It's because it's the same range R. Well, yeah, the difference would be that event C, violates both, has both for a fixed R. But what you're saying, probability of B is greater than equal to probability of C, which is equal to probability of A and C. Sort of your comment is sort of implicit in that part as well. Okay, so oh, brilliant, brilliant. Okay, so here's a different way to generate the samples, right? I can sample 2K points first. So I sample all of them first, and then I divide them into two parts evenly. Okay? So that is what we'll do. Okay? And what's there to say? We'll find out. Okay, so let's look at the probability of B. Okay? So here I'm summing over all the possible ways to sample Q0 initially and breaking it up, right? So it's conditional on Q0, what are the odds of probability of B? Okay. And, sorry. And that's of course at most, what is it, whatever is the worst stat. And, okay, so now our goal is to prove that for any fixed initial sample, the odds of B happening is at most 1/4. Okay. Okay, so what's the advantage of B given Q0? What's so helpful about the given Q0? Yeah. Yeah, so there's only a limited number of ranges induced by Q0. So I'm worried about the two samples getting any range out there wrong. But I've already kind of restricted myself to this set of 2K points, and I only have to worry about G of 2K uh, ranges, right? This is just this brilliant double sampling trick. And okay, so as you pointed out, so this the number of different ranges induced by Q0, you've already said, whoa, that was a lot. Okay, whatever. um, is at most g of 2k, okay? And we've chosen k big enough that you can just apply uh, the additive turn-off bound to each of these, okay? So for any one of these ranges in Q0, if I'm letting mu0 denote the measure in Q0 now, okay, so mu1 is for Q1, mu2 is for Q2, and mu0 is for this initial sample of 2k points. What are the odds? Okay, so mu1 is going to be pretty close to mu0 by the additive turn-off bound. So your sample of Q1, which is sampling out of Q0, is going to look a lot like the Q0 sample for a particular range. Same with mu2, it's the same, right? And k is big enough that you can take a union bound over all G2k shapes. So here I've just plugged in the e to negative 2 epsilon squared. I've plugged in for n, you know, this choice of k, which is like, log of G2k and stuff, divided by epsilon squared. Okay. So, okay. So, so by the union bound, you're going to get all of these sets correct in a certain sense. And what's left? For all sets, yeah. If I look at the difference, right, I can write that as the two differences relative to Q0. And then this is at most epsilon. Should be at most epsilon. There it is. Okay. Right? That's what we wanted. And the nice thing is that this was just all the ranges induced by Q0, but that gives you all the ranges out there. Because all the ranges out there, they project onto Q0 first. And then you ask if they're different on mu1 and mu0. Right? So we're able to take this union bound over all the disks in the universe by first projecting onto the 2k size sample first and say, well, now there's only a so many disks I'm going to distinguish anyway. And I can take a union bound over those. Right? This is wonderful. And yeah, so that's the result. Okay. Right on time. So so that's how you get the epsilon sample theorem, this double sampling, which really lets you reduce your union bound, the number you're union bounding over, to something relative to the growth function. The epsilon net theorem, you can imagine trying to do a similar trick. Maybe some details will change, some calculations will change. So naturally that will be on your homework, right? But it should be kind of like trying to transfer this to a slightly different setting. So hopefully it'll test your understanding of this. And then what we'll discuss this time is how to bound the growth function for some simple classes and stuff like that. It's not so much randomized, but it's useful for randomized. And it'll bridge the way to some learning theory that we'll do on the other end. Okay? All right, so that's it for today. Thanks, guys. Let's have fun. Okay, so let me remind us what we did last time as people trickle in. So we were looking at some geometric stuff last time. Well, first we introduced the additive turn-off bound. It's like multiplicative turn-off bound, but it's additive. You can compare and contrast the two. Here I'm looking at something like 1 minus epsilon times mu. Here I'm looking at something like mu minus epsilon. They're very similar, but a little different. Morally the same. Okay, what we really talked about was these epsilon nets and epsilon samples, which was coming in this weird range space framework. This is where you have points in some shape, in some space, and you have ranges which are like shapes, right? So simple examples included like intervals containing points on the line, disks containing points in the plane, hyperplanes in high dimensions or in the plane, right? And And so the kind of question that often comes up is something like, oh, uh, imagine you're a computational geometer, you have a bunch of points in a plane or something, you have a disk, and you want to know, oh, how many points are in this disk, right? This is a very common kind of thing. And so we were sort of interested in developing random sampling that's good for these kinds of queries. So the framework we posed it in was we have this notion of measure. So for a range space R, the measure is what fraction of the points are in the range. Okay. And if I take a subsample, then I can look at that relative fraction instead. So if I have some subset Q, I can write the measure with respect to Q instead, right? But there's just a percentage of points. And the idea is, okay, if I'm going to sample a subset of points, and I want to roughly preserve the measure. So if a disk had half the points originally, I want it to have close to half the points in the subset, right? How big does the subset need to be? Okay. And right, the two ways we quantified this, we really focused on the first one. How big does it need to be if all the measures are off by an additive epsilon? Okay. And then a slightly different version that's sort of like heavy hitters is for every range that has at least 10% of the points, can I make sure I hit every single one? Okay. And the first simple observation is that if you don't have any assumption on your ranges, then you really can't do anything interesting, right? So let's say that you want to get like an epsilon sample for 10%. If the ranges include all possible subsets of your points, then we can just make a range with like whatever points you left out, right? If you're leaving out more than 10% of the points, and then you'll be off by more than 10%. Okay. So if you don't have any structure on the ranges, you really can't subsample down and try to and hope to preserve every single set in any meaningful way. So that's why we start looking at, so the hard case is like these ranges that can shatter the point set, right? It does every single subset, but that's not true for many natural cases, right? If I have if I only have disks in a plane and I look at the subsets induced over the points, right? Like, okay, I can capture like these 3 points, and I can capture all 4 points with a disk, right? I can induce that subset, this subset, subsets like this, right? I can do some of those subsets, but it becomes awfully hard to do diagonals, right? It's not clear that I can go draw a circle that captures these 2 points, right? Or if you did, then it would be hard to do the other diagonal. One of the 2 diagonals are going to give you a hard time in this picture. Okay? So many natural range spaces that come up aren't nearly as hard as all possible subsets. And that gives us some hope. So we analyze stuff parameterized by something called a growth function. Okay? So a growth function is like, okay, if you have 20 points, how many possible subsets can it induce for some family of ranges? So if your family of ranges is circles, at some level, any 3 points, you can kind of squeeze a circle until it's tight around 3 points. So it's not too hard to see. We're going to make this a little more formal to show that if you have n points in the plane, the family of all possible disks can really only induce n cubed distinct subsets. Okay, so that's far from 2 to the n. Okay. So now if you want to start doing epsilon nets and epsilon samples, you can start just taking a union bound over these things. So if I start with like n points and I know it's disks, I know there's only n cubed regions I have to really worry about, or n cubed subsets. So I can just choose my k to be large enough to be able to union bound over this, right? So you can always do g of n, where n is the growth, g is the growth function. So that's easy. But what we did was way cooler, or I don't know if cool is the right word. Yeah, it was way cooler. So look at this epsilon sample theorem. It says that, okay, it's a little bit weird. I wrote k is greater than or equal to the growth of 2k. So you have to choose k big enough, or log of g of 2k. So you have to choose k enough to be true, but I've plugged it in. So if the growth function is polynomial, if it's n to the d for some d, If you choose k to be at least d log d over epsilon squared, then you're going to get an epsilon sample. You're going to preserve the measure of every range up to an epsilon additive factor with constant probability. Okay. But what's so interesting is that it's independent of your input size, right? You're trying to preserve the weight of every single disk ever. And it's saying you would think that if you had more points, that should be harder. But it's saying no, it doesn't matter. All that matters is this growth function, and really, it's sort of the complexity of the range space, right? So g of n is less than or equal to n cubed. That's really some comment about the geometry of circles being simple, right? It's a relatively low complexity object, and it's just that complexity that determines the size of the sample you need. Okay, so that's really cool because it's independent of the input size. There's a similar epsilon net theorem that you're going to prove on the homework. Okay, so if you just wanted to make sure you hit every set with range at least epsilon, then you only need one epsilon instead of epsilon squared, but it's pretty similar. So that's what we did last time we proved this thing, and it was based on this really clever idea of double sampling. Okay, so this idea that, oh, you know, at some level, instead of focusing on, let me sample k points and see if it gets everything right, let me sample two sets of k and see if they kind of agree on each other, with each other, right? That's what we reduced. That was that first step within a factor of 2. And then you take that and you reimagine that as, oh, well, let me first sample 2k points and then split it in half and see if the two halves agree with each other. That's the exact same way to generate two samples of size k. Okay? But the advantage is that if you do the 2k points first, now there's really only g of 2k shapes or subsets at play. So instead of having to do a union bound over g of n, you're doing a union bound over g of 2k. Okay, and then just making the two halves match. Okay, so this double sampling trick is really clever, but let's just go from union bound over g of n to union bound of g of 2k. Right? So anyone here who's doing machine learning knows how important this is. Okay. We might touch on that today, but maybe more next time. So that was the high level idea of the proof. Okay. And we left with this fun question. How do we bound g of n for various different shapes? It's not really a randomized question anymore. We're do some geometry and stuff, but of course it's relevant too. Okay, so yeah, this is one of these things. I think my presentation could be better, so feel free to think of better words for things as we go along the way. Okay, right, so this is when we're going to talk about VC dimension. Okay, so a VC dimension is about shattering. So if I have some setup points and I have my range spaces, I'll say that the ranges can shatter the point set if it can induce every possible subset, if it really hits that worst case. Okay, so again, this R intersection or R and Q is sort of projecting R onto Q. So it's all of the intersections of a range in R onto Q. And so if that recovers all subsets, then we say it shatters it. Okay. So the VC dimension is the maximum cardinality of any point set such that R shatters that point set. Okay. So sort of weird definition, but let me give you maybe an example. Okay, so let's take points on the line. Okay. So and intervals, right? So our subsets are all possible intervals. So what is like the largest number of points that intervals can shatter? 2. Anyone else feel? 2? Okay. That means we should be able to come up with 3 points that you can't shatter, right? So Okay, so these points here, right? Obviously, you can shatter the individual sets, so you can get singletons, you can get the whole thing, you can get parts like this, right? But the tough case is if you wanted to do these two together, right? So this kind of thing, right? You can't find an interval to contain those 2 points. So bummer. Okay, so uh, guess I should have written two based on my definition. Okay, so it's two. Okay. Unless VC dimension means it's the largest cardinality you can't shatter. Maybe I should check and make sure we're consistent. It's can shatter. Okay, so it is two. Okay, good. All right. What about disks in the plane? Three or four? Three? Okay. Um, it's two. So I think the points need to be in general position. So that means that we can assume they're not on the line. Okay, so if none of the points are on the line, like three in a row, yeah, because otherwise you can't deal with that. Uh, okay, so if you have any 3 points, can you shatter it? Okay, so one sec. Let's look at these three. Uh, we can put all of them together. We can obviously do each one individually. Here's two. Here's two. There's two. Something like this. Okay. Uh, now how about four? Okay, so here's one case where you're kind of screwed. So what happens? So here they're not in convex position. I have 3 points, and there's 1 point in the convex hole, and it's very hard to capture the outer 3 points and not get the middle one, right? So if I wanted to find a set that contains these 3 points, okay, I can't do that with a circle because a circle uh, is convex. So if it'll contain everything in the middle, and the middle is in the convex hole of the three outer points. Okay, but you have to show that any possible set of four you can't do, right? Yeah. You want to transform that into a convex? Uh, so I think because because I think the way the question. Okay, so can we like map it or something? If the goal is to capture this with circles or something like this. Um, so I think part of the idea, because you can always map anything into a super high dimensional space and do whatever you want. So I think the question is that we're making a commentary about this set of shapes in this particular geometry. So to change the geometry or to just warp it into some higher dimensional space is just asking a different question altogether. But well, okay, so if you're doing a learning algorithm, and at the end of your day, your algorithm can only output classifiers that look like disks. It's going to be able to answer some sets of labels correctly, but not others. So it's going to have a tough time with a data set that might that might label the outer 3 points as true and the inner one as false or something. If it can only, say everything inside a circle is true. So so this will help us analyze particular algorithms that are already working in geometry. It might then motivate us to say, well, this geometry is not strong enough. Why don't we do a more sophisticated algorithm? Yeah, yeah. Say, okay, what if I could have rings, right? If I can have a disk and a disk inside or something, I could definitely deal with this. And then we would try to analyze the VC dimension of rings, stuff like this. Yeah. These are just simple examples. And in fact, VC dimension is actually very nicely well behaved under things like, oh, I have two set systems. What's the VC dimension of all pairs of one set from here and one set from there? Or intersections or unions and stuff. And uh, yeah, so it's there. Now, we need to be able to rule out for this particular geometry all 4-point sets. So there's one other possible configuration. That's 4 points in convex position. Okay, so in one case it's not in convex position, that's on the left. In the other case, they are in convex position. In that case, you'll find that you might be able to do one of the two diagonals. I guess that's this one. But then you're going to have a really hard time doing the other diagonal. Okay, if you could do, but then you might say, okay, well, why does it have to be uh, a disk? Why don't I do an ellipse, right? And it's like, well, that's a good point, but that's just a different question. You know, we can have a different question of what's the VC dimension of ellipses. Okay, let's see what I wrote here. So I seem to be off by one. Okay, so so this should be 3. All right, half spaces. What's the VC dimension of half spaces? Say in the plane. D minus, so this is 2 dimensions. So you can shatter any set of 1 point. So it is related to D. So what is it in two dimensions? You can work it out on paper. You have a whole notebook. So you can shatter any 2 points, right? We can just draw a line in between. So we want to find the largest. Yeah. Can you? Yeah. Can you? Yeah. How big of a set can you make that you can still shatter? That's the question. You can't shatter 3. So we just have to come up with 3 points. So let's say there's 3 points up on top. Okay. So if it's like these 4 here, you know, it seems like it's hard to shatter these 2. I mean, to set apart those 2 from the other 4. Something like this. Yeah. So there is a more general thing based on what's called Radon's theorem. Radon's theorem, that is, if you give me a set of D plus 2 points in RD, so I guess 4 points in the plane, I can split them into 2 parts so that their convex holes overlap. Okay. And a hyperplane is convex. So if a hyperplane is like containing S1, then it must overlap also with a convex hole of S2, which means it has to have at least 1 point from S2. So Radon's theorem is the theorem in high dimensions. Of course, on the plane, you could probably just write it on paper and convince yourself. Okay. Good. Good. So that gets you VC dimension, yeah, D plus 1. Because D plus 2 you cannot do. Okay. So now we just need to relate this to the growth function. Why are we interested in VC dimension? So I guess the idea is that VC dimension is like intuitive, like you might be able to infer the VC dimension of a general shape. But ultimately we want to relate that to the growth function. Okay. So that's called Sauer's lemma. It says that if something has VC dimension D, then the growth function is at most n to the D. Okay, so the summation is slightly more precise. That's actually, we need the precision because it's going to be a proof by induction, so you need to do it very carefully. Okay. So intervals is n squared, disks n cubed, half spaces in RD, Gn is less than equal n to d plus 1. So you need roughly d points to do those epsilon nets and epsilon samples. So lots of algorithms using the quote-unquote kernel trick is going to take the points and transform it into really high dimension and then look for a half space. All right. So good, good. Um, great. Okay, so this proof is this is like the one time that linear expectation is not the answer. We're just going to like slowly go through this and do some combinatorics together, and it's always confusing. So that's something to look forward to. Okay, so just so I don't have to write the summation again, I'll write fd of n is equal to this term. Okay, so we're trying to show that g of n is less than equal to fd of n. We'll kind of do it by induction on d and n. So like, what are the base cases? This is usually an easy one. What would be a base case? Huh? Yeah, or equals 0? Yeah. Let's see what I wrote. Um, okay, so if the n is 0, then of course there's no subsets you can induce, and that's okay. You can double check. If d is 0, then g of n is at most 1. You can only do one set. Uh, right. Okay. Uh, good. Okay, so now the interesting inductive step requires this like really funny thing. Okay, so I'm looking at a general n and larger d. So I'm going to fix a set of n points, and I'm going to pick out one point in this set. Okay, and the proof is going to try to like remove p from q and then analyze that. And it does this in like the weirdest way possible. So we're going to create two subsets of ranges. So one is like, okay, what are the ranges that don't include p? But also r plus p is in R. Okay, so that's like, I don't know how to draw a good picture. It's like, okay, so you have this point Q, and you're looking at like ranges R that where this is a range, and also the one that just also includes R. This is also a range. Okay, so these are ranges that don't include P, but also if you had included P would be a range, which is, yeah, could have been written alternatively as. Um, okay, and then the other ones, the other set of ranges we're going to create, okay, is uh, I'm just going to, these are both going to be range spaces over a subset of points. So I'm just going to take all the ranges in R and remove P. Okay. So this will give me two range spaces that all exclude P. Okay, two different sets. Now, yeah, so this is really a counting argument. All right, so this is where counting comes in. So the claim is that, okay, so this is two families of ranges, all of which exclude P. The claim is that the size of RP plus the size of, oh, they're both RP, aren't they? Well, the two sets, they add up to the original one. I have a proof written down, but maybe someone else can just stare and come up with a better one. I should mention we're already just assuming that R is we've already projected onto Q, so they're all subsets of Q. Yeah, yeah. So none of them have P. Now on the right, there's two. Okay, there's at least two different kinds of sets on the right that might not be included on the left. One is a range like R minus P itself might not normally be a range. R was a range. It's a disk, and I say, oh, disk minus point. That's not necessarily a disk. Okay, so that's one kind that's getting included, and it can also be ranges that didn't have P to begin with, but that range plus P was not a range. So on the left, it's yeah, it's a little bit weird. But yeah, does anyone have a good? I have a cumbersome explanation, uh, but it's cumbersome. Okay, I would say something like, okay, if for R and R, we have three cases. Case one, P is not in R, so this point already excludes P. And if I had added P to the range, it would not be in the original range space. Would not, just like I said. Okay. Um, and that would imply R is in too much R's. R would be in which one? I know the answer is RP, but which RP? Okay. Case two. P is not in R, and R plus P is in R. What would that imply? Okay, so these are actually getting double counted. So that's not a good sign. Okay. And this is like some mean joke where it's just like a bunch of combinations of R and P, and I just decided not to use any other letters. Okay. Case three. P is in R, and R minus P is in R. Uh, I'm a little worried about my definition too. What were you saying? R sub P, R superscript. But you can have two sets that go down to one. Yeah, yeah. I'm also concerned. Well, okay. So it can only satisfy. Uh, so there's a little bit of like. So in the last two, there's a little bit of like complementarity, right? So if P is in R, then only the third thing matters. R minus P is in R. If P is not in R, then only R plus P in R matters. One is wrong. R plus P is not in. So I'm okay with number one. So R is a range, P is not in R. So R minus P is just R. And so that's in the second set. This should be a plus. In particular, it's not in the first set, right? Because R plus P is not a range. I told you this is going to be a terrible explanation. Yeah. Uh, okay. Okay, I think I understand what you're saying. Or maybe here's another explanation. Imagine you start with R, right? And at some level, you first want to make a range space that doesn't include P. So I'll say, let me just take all the ranges and remove P. And then I would get R to the P, super P. Okay? And then I would say, okay, but now there's some double counting. I mean, there's some colliding, right? The number of sets has gone down because if sort of like, let's say R had P in it, but if there's also another set that's the exact same as R but didn't have P in it, they map down to the same thing when I remove P. So the things that map down should be in R sub P. So R sub P are the ranges kind of in the smaller space where if you're expanding back out, you could add or not add P. So you start with a range space that includes P, right? And now you create a range space over all the points except for P by just taking all your ranges and removing P. Now you're going to get some collisions. There could be ranges where if you had removed P, it's equal to another range, right? Which on the other side is like a smaller set where adding or not adding both give you ranges in the bigger set. Okay. So R to the P just first maps down, and R sub P is sort of accounting for the things that collided. Okay. Okay, good. That's better than perfect level of hand waving. But are we kind of okay with this? This actually makes way better sense to me, so I'll rewrite this later. Okay. Thank you. Okay, good. We're making progress, guys. We're doing science. We've improved the state of the art. Okay, so we have this thing. Okay, this counting argument. Now, okay, if okay, so let's say R originally over the original point set had VC dimension D. Okay. Now, maybe the second one we should do first. So the second one is I just take, or maybe either one's fine. Well, let's do the second one. So first I take my original range space of VC dimension D, and I make a new VC dimension, I mean range space omitting P by just taking all the ranges and removing P. What's an upper bound for that VC dimension? Well, still at most D, at the very least, right? The VC dimension doesn't go up. So that one's actually not so interesting. The more interesting one is the first one. So these are the particular ranges in the smaller space where two different sets map down. One set that included P and one set that didn't. What is the VC dimension of this? D minus 1. Because if I can shatter like 10 points in a smaller space, right, I can add P back to the shattering set because for every subset that included P, I had a subset that it didn't include P. So that's the key point, is that in that collision set, the VC dimension goes down by 1. And now, when I start doing this thing, we imply this thing by induction. Okay? And you get this kind of thing. And what's the difference between these two terms? Oh, there should be I equals 1 to D, I think. But it's okay. We'll see what happens next. Um, okay, so let me write it this way. Uh, right, right. Okay, that's fine. So this is an equality. All I've done is shift it up by 1 so that they both sum to D. So, okay, I know the answer. So why is this sum less than equal to this sum? Okay, so what's the Pascal's triangle argument then? Imagine I don't know the name of anything. I just like can reason. So this is the number of ways to choose at most D items, right? And this looks like it's saying, well, if you choose the first item, this is the number of ways to choose D minus 1 items. So that's using the first one. And this one's saying you don't use the first item, and then you have how many ways can you choose at most D out of the remaining n minus 1. Maybe that's what Pascal's triangle is. I don't know. Okay, right? And that's FDN. Okay. So it seems like the key idea is this observation that when you project down, when you're removing a point, you have your set of projections, and then you have that subset for the double collisions. For the colliding things, and there the VC dimension goes down, and that's where you start getting an interesting bound. Yeah, so let's say that R sub P can shatter 9 points, right? So some set of 9 points. And now these are like whatever sets I used. I know that in the original space, I have that set without P, and I also have that set with P. So I can shatter with P or without P. So I can always add P to a shattered set, to the shattered set of points, because you have this toggling for P. Yeah. And that seems to be where, because somewhere along the lines, we outcomes this polynomial, effectively polynomial bound, right? And I think that's where D goes down, and that's where you're making progress to get this stronger bound. Okay, so that's the proof. Yeah, I feel bad because this class called randomized algorithm. That was neither randomized nor an algorithm. However, it does tell you that if you have VC dimension D, you only need D over epsilon squared points or so to get an epsilon sample. Okay, so if you have your linear classifier in high dimensions or something, you need a point set based on your dimensions. Um, all right, any questions? So what I was going to do is get the next topic started, which is closely related to this, so that you're all excited to come back on Friday.